Hi everyone, welcome to this class. In this class, we will talk about the second part of chapter 1, so the classification of optimization. In this part, we will mainly talk about how to do classification for optimization problems and then pay attention to convex optimization. Finally, we will present what is algorithms. Now, actually, there are different kinds of optimization classifications. They divide optimization problems into different ways. For example, we have constraint and unconstrained optimization, and we got continuous and discrete optimization. Also, global optimization and local optimization, and also stochastic optimization and deterministic optimization. Finally, is the convex and non-convex optimization. In the following, we will discuss them one by one. Now, for constraint and non-constraint optimization problems, they are actually depends on whether there are restrictions on the problem. Okay, so if there is no restrictions on variables, then we call it unconstrained optimization. If there are restrictions on variables, then it is actually a constrained optimization problem. So if you look at this figure here, and for figure A, you got no restrictions on x. Okay, so this is the curve of function values. And for the variables x, it is the all R dimension space. And for figure B, we have some restrictions on variables. So we require the interval must be between A and B. In other words, for figure B, it is constraint optimization problem. So it is easy to see that for unconstrained optimization problem, it may be easier because there is no restrictions on variables. However, for constraint optimization, you may design complicated algorithms because you have to take care of the restrictions. Right, let's take a look at continuous and discrete optimization. For continuous optimization, it actually means that the feasible region is uncountable infinite. In this case, we call it continuous optimization. For example, you got a feasible region like this. The dark part is the feasible region. Of course, there are uncountable infinite points in this region. So for this case, the problem is a continuous optimization. However, if not, or if the feasible region contains finite number of points, then we call it discrete optimization. For example, you got the feasible region as the dotted point. So for this dotted point, these are the feasible region of this problem. In this case, it is called discrete optimization. So what is the theoretical difference that discrete and continuous optimization will make? As we can see, for continuous optimization, the benefit that you can have is you may use the local information, okay, to estimate the status of the point. However, for discrete optimization, it is not that easy to use neighboring information because even the 2 points, they are neighbors. There may be great changes from this point to this point. So this brings potential difficulty to solve discrete optimization. So as we can see, discrete optimization may be more difficult than continuous optimization. In the following, we give a very typical class of discrete optimization, which is called integer programming. Integer programming actually deals with variables whose value would be only binary or integer. So if the variables, they can choose only integers, then it will be called integer programming. For example, whether or not we put a factory in a certain city, this will be an integer programming. We will use an integer variable to denote these decision variables. In this case, it will be integer programming. Now, let's take a look at the third part of classification. Actually, it is global or local optimization. Okay, so the difference between global and local optimization are actually the aims. Okay, if you are seeking for local optimizers, then it is actually local optimization problem. If you are trying to seek the global minimizers, then it is called global optimization. For example, I plot a figure here, and this is the curve of the function values. So you can see that there are many values here, right? And for each value here, there will be a local minimizer. And of course, we can find that 0 is the global minimizer. Okay, so this is the local and global minimizer. So roughly speaking, what is local minimizer? Local minimizer means that at this point x, the function value have reaches the lowest value within a neighborhood of this x. Then x will be a local minimizer. In contrast, if at point x, the function value reaches the lowest values among all the feasible points, then it is called the global minimizer. So this is just roughly speaking. We will talk about more details about local and global minimizers in Chapter 2. Now, let's take a look at stochastic and determinist optimization. First, let's take a look at this optimization problem. So we got objective, and also we got decision variables in n-dimensional space. Finally, we got some restrictions, which is equality constraint. So to find this x, this vector c and b are parameters of this model. In other words, we need to know c and b before we solve this problem. However, in some real applications, c and b may not be totally known when we solve this problem. In this case, c and this will be called the stochastic optimization. Otherwise, if c and b are totally known before we solve this problem, then we will call it determinist optimization problem. Finally, let's talk about convex and non-convex optimization. So, what is convex optimization? Roughly speaking, you got convex function for minimization problem, and also the convex feasible set. If the two issues are satisfied, then the problem will be called convex optimization problem. Otherwise, it is non-convex optimization problem. Let's take a look at the two curves here. And for this function, we can actually know that this function is a convex function. And for this function here, it is non-convex because you got many local minimizers here. We will talk about convex optimization in more details in the following. Now, to talk about convex optimization problem, the first definition we need to know is the convexity. Let's first introduce what is convex set. So what is convex set? If you take a look at the four figures here, can you identify what are the convex sets among them? Yeah, the first one, the second one, they are convex set actually. Why? Okay, so before we introduce the mathematical definition, let's take any 2 points in the figure and we draw the line segment between the 2 points. If the line segment entirely lies in this set, then this set will cause a convex set. Now, for the 2 convex sets here, it is convex. However, if we draw 2 feasible set points here, and the line segment may not lie in the set. So in this case, the 2 sets is not convex set. Okay, so the mathematical definition for convex set is actually like this. If for any 2 points in this set S, the following point also lies in S. So what is the following point means? It is actually called the convex combination of the 2 points. In other words, if the convex combination of the 2 points still lies in this set, then this set will be convex. Okay, so notice that for convex combination, the definition requires that the coefficient, the 2 coefficients here must be non-negative and must be smaller than 1. And also the sum of the coefficients must be 1. So this is the convex combination. Right, after the convex set, we can introduce what is convex function. So what is convex function? Convex function actually, first it must be defined on a convex set, capital S. In other words, its domain of this function must be convex. Then fx must satisfy the following inequality. So what is the following inequality means? So if you still remember the convex combination, then this condition actually means that the function value of convex combination is not greater than the combination of function values. Okay, it's not greater than the convex combination of function values. So this is what the convex function means. I also draw a figure here. So basically it means that the curve of function value must lie below the line segment of the 2 function value here. For convex functions, we also got a similar definition called concave function. So f is a concave function means that the minus f is convex. Okay, so the definition is very simple. And we got several examples for convex functions. For example, the linear function. Okay, so linear function is a very special function. It is both convex and also concave. Secondly, for convex quadratic function, which is defined as the x transpose hx, if H is a symmetric positive semi-definite matrix, then the function f is called convex quadratic function. Otherwise, if H is not positive semi-definite, then it is not a convex function. Alright? Now, we also have some properties of convex function. For example, the sum of 2 convex functions, they are also convex. And also the positive scalar of convex function is also convex. The 2 equivalent conditions here actually characterize what is convex function. For example, if f is continuously differentiable, in other words, we got gradient, then the convexity can also be equivalent to the condition here. Okay, so for this condition, we actually characterize the convexity by the gradient. We can use this equivalent condition to characterize the convexity. Moreover, if f is twice continuously differentiable, we can also use the second order information to characterize the convexity. The second order equality condition is that the Hessian matrix here is positive semi-definite. Alright, so these are the two equivalent conditions for convex functions. They will be used quite often in our class. Now, let's take a look at convex optimization. So for convex optimization, as we mentioned before, the function must be convex and the feasible region must be convex. So in terms of equality constraints and inequality constraints here, so the corresponding requirement becomes this equality constraint Ci must be linear function. And for inequality constraints, we must require this Ci to be concave function. Okay, so please note that here, for inequality constraints, it is greater than or equal to 0. So in this case, this Ci must be a concave function to make it a convex region. Right, so this is the requirement for convex optimization. In this book, we will mainly focus on convex optimization. Okay? Now, finally, let's talk about numerical algorithms. So what is optimization algorithms? Optimization algorithms is actually a kind of loop. Okay, so it starting from initial point x0, and it generates the next iterate x1, then x2, and so on. So the key point you can see that is how we generate the next iterate at the current iterate xk. After we figure this out, then the algorithm will start and we can run it. And also there are several ways to measure the algorithms. The first one is robustness. Robustness actually means that the algorithm, whether it performs well on a variety of problems and based on reasonable values of starting points. Okay? If an algorithm can be applied to a large amount of problem and also it can be started from many initial points, then it can be viewed as robust. Otherwise, it will not that robust. And for efficiency, it actually means that these algorithms take less CPU time and also take less memories, because the CPU time and the memory are valuable resources in computational aspect. Now, finally, is the accuracy. Okay, accuracy means that what is the returned solution by the algorithm close enough to a true solution. Okay, if it is exactly the true solution, of course it is good. However, in real computational algorithms, people will always have some arithmetic rounding errors. Okay, so it means that basically the returned problem is actually not the exact solution. So we need to do some accuracy analysis, and we actually assume or we hope that the solution will return a reasonable accuracy statement. Okay? Right, so for this lecture, we stop here and let's make a brief summary. And we introduce the different ways to classify the optimization problem. And we talk a little bit about what is convex optimization. Finally, we end up with numerical algorithms, how it works, the rough idea. We will talk about more about convex optimization and algorithms in chapter 2. Okay, so we stop here and see you next time.